Compound characterization. Infrared spectroscopy, characteristic stretches. This is the slide we used to end the previous webcast on the background to infrared spectroscopy. In that webcast, we discussed how we can use infrared spectroscopy to identify functional groups within a molecule because certain bonds absorb certain wave numbers of light. You can see a small subset of that here in this yellow box. Of course, organic molecules can contain many other types of bonds other than what's listed in this box. In this webcast, we will talk about common bonds you find in organic molecules and the typical absorbances you can expect to find them at. This slide contains an image and a number of tables. If you own a Chem 233 lab notebook, you can find this image and these tables on the cover of your lab notebook. If you do not own a Chem 233 notebook, you can find a copy of these tables on the Compass 2G course website. What do we have here? Up top, we have what is being called a generic infrared spectrum. By generic, all it means is that it is showing many of the common types of absorbances that you can find in an infrared spectrum. Up to this point, you have heard me refer to each of these peaks as absorbances or signals. Another way to refer to these is using the word stretches. Remember, these peaks result from bonds stretching as a result of absorbing certain wave numbers of light. How does this image correlate to the tables down below? This image is divided into a number of different regions based on letter, A, B, C, D, and so on. Each letter corresponds to a particular type of stretch. For example, the letter A corresponds to OH and NH stretches. This is the first thing that you should get from this slide. Different bonds can have absorbances that appear in the same region. They can overlap. As we can see, OH bonds and NH bonds overlap quite a bit. If that's true, how can you say whether a stretch in this area belongs to an OH bond or an NH bond? Well, to do that, you're going to need different information. We'll talk about that type of information in future webcasts. The second thing you should get from this slide is that stretches don't appear at a particular wavelength. They appear in a range. If we look again at the OH stretch, it doesn't appear at just, say, 3,400 wave numbers. It's anywhere between 3,200 wave numbers and 3,600 wave numbers. Similarly, if we look at the F region, which corresponds to carbonyl stretches, we see that they can appear anywhere between 1,650 wave numbers to 1,785 wave numbers, depending on the type of carbonyl. Does the fact that a stretch can appear at different wave numbers tell us something about the type of functional group? It actually can, and we'll talk about that in relation to carbonyls later in this webcast. Now, this slide contains a ton of information. Do I expect you to memorize every single box on this table? No. What I expect you to memorize are the general ranges for the most important of these stretches. Let's talk about those stretches here. On this slide, I have an empty infrared spectrum, and what we're going to do is we're going to fill it in piece by piece with the most common stretches you might see in an infrared spectrum. The first piece we're going to look at is from 1500 to lower wave numbers. This particular region is called the fingerprint region. The fingerprint region tends to be very crowded. Many different types of absorbances appear in this region. This region is often very difficult to interpret correctly. As a result, whenever you are interpreting an infrared spectrum, I strongly recommend that you do not attempt to interpret the fingerprint region. The reason we call this the fingerprint region is because it is characteristic of a particular compound. Because it is so complex, it acts as a fingerprint for a particular compound, and we can use it to identify it. The next region to look at is at approximately 1,650 wave numbers. In this region, we see carbon-carbon double bonds. Now note that this is approximate. Carbon-carbon double bonds can appear above 1650, they can appear below 1650, but they will always appear somewhere in this area. The next region to be on the lookout for is at approximately 1700 wave numbers. This region we see carbonyls. Again, carbonyl stretches might be above 1700, they might be below 1700, but they should be somewhere in the area. The next region to look at is at around 2200 wave numbers. Here, we will find carbon-carbon triple bonds. But there is a caveat here. If you look at the table on your lab notebook cover or on the course website, you will notice that for the carbon-carbon triple bond, it says that the signal for the carbon-carbon triple bond might be weak if the carbon-carbon triple bond is too symmetrical. Why is that? Remember, a bond is IR active if there is a change in dipole moment as it stretches and contracts. If a carbon-carbon triple bond is too symmetrical, there isn't a large difference in dipole moment, which means that even if it stretches and contracts, there isn't going to be much of a change, and so it won't appear, or if it does appear, it won't be very large. As a result, carbon-carbon triple bonds might not appear in an infrared spectrum even if they are in the molecule. How will you know whether it appears or not? You won't, and so you'll have to use other spectroscopic methods to corroborate your conclusion. This is one of those exceptions I mentioned at the end of the last webcast, and you have to be careful with it. The next region to look at is at 3000 wave numbers. Here we find CH bonds. The type of CH bond, however, is important. If the carbon in a CH bond is sp3 hybridized, then it appears below 3000. Typically between 2900 wave numbers and 3000 wave numbers, although stretches can go below 2900 wave numbers. However, if it is sp2 hybridized, then it appears just above 3000, say from 3000 wave numbers to 3100 wave numbers. And that's incredibly useful. Whether a CH stretch is above or below 3000 tells us what type of carbon we have in that bond. Similarly, if we have an sp hybridized carbon, that's even further above 3000, usually at around 3300. Although again, it can be a little bit above or a little bit below. This is an example of how the same type of bond can appear in different parts of the infrared spectrum based on what comprises the bond. The sixth and final region is not really a particular wave number, it's more a block. From 4000 to can be as low as 3000 or even lower, is where we find OH bonds and NH bonds. The reason that these types of bonds can appear in such a wide area is because their shape is different than the shape of most other stretches. The shape of an OH or NH stretch tends to be quite broad. In contrast, the stretch for most other bonds, say a carbonyl, tends to be quite narrow, like I'm drawing here on the right. And that's another important thing to know about an infrared spectrum. The shape of a stretch can tell you what type of stretch it is. Most stretches will be quite sharp and distinct. You can immediately identify an OH stretch or an NH stretch because they will look different. They will tend to be much broader than most other stretches. While I do not expect you to memorize the tables I showed you on the last slide, I do expect you to memorize these 6 regions. Now let's take this knowledge and put it to use by interpreting an infrared spectrum. Here is the infrared spectrum for aspirin again. Let's look at this step by step. Remember that the fingerprint region is 1500 wave numbers and lower, which means we are not going to try and interpret any of this. And frankly, that comes as a relief to me, because look at all of these stretches. Look at how difficult it would be to try and interpret these. So we ignore all of that. Now let us look at the next region. Let's look at roughly 1650. Do I see a stretch there? Indeed I do. Therefore, there is a carbon-carbon double bond somewhere in the molecule. Is that true? In fact, there is. I have several carbon-carbon double bonds. These carbon-carbon double bonds give me this stretch. Okay, so that's the carbon-carbon double bond region. Now let's look at the carbon-oxygen double bond region. Do I see anything there? That's at roughly 1700. And indeed, I do. I see 2 peaks in that region. That means I have a carbonyl somewhere in my molecule. And I do. In fact, I have 2. You might be wondering, why do these 2 carbonyls show up at different locations. We'll talk about why that is on the next slide. Now let's look at the next region. At 2200, I would see stretches that correspond to carbon-carbon triple bonds. Do I see any stretches in this area? No, I don't. Therefore, I probably don't have any carbon-carbon triple bonds. Now remember the caveat that I stated. Just because I don't see a stretch here does not mean there isn't a carbon-carbon triple bond. But it's a very good indication that I don't have a carbon-carbon triple bond. Okay, now let's look at the next region. Let's look at roughly 3000. What do I see here? I see a bunch of stretches below 3000. That means I have sp3 hybridized carbons attached to hydrogens. Is that true? Yeah, I have those here on the methyl group. Okay, do I have anything above 3000? Well, that's kind of hard to say. I do have this region right here. There is a stretch of some kind here. But what does that stretch correspond to? It's actually difficult to say, and that's because in this region, we actually have stretches overlapping with each other. This very broad stretch corresponds to the OH located here. Unfortunately, that stretch is overlapping with what we should see for these sp2 hybridized carbons attached to hydrogens. The stretches belonging to these bonds are present. Unfortunately, they are being covered up by the stretch for the OH. This is an important lesson to learn for IR spectroscopy. Stretches corresponding to different bonds can overlap with each other. Hopefully, interpreting this IR spectrum is now no longer as intimidating as it once was. You now know that everything here on the right side of the spectrum is not interpreted, which makes our work much easier. And you saw how each of these other clearly defined stretches corresponded to bonds present in aspirin. You also learned that the stretches for different kinds of bonds can overlap with each other and how it is important to be aware of that possibility. Let us discuss carbonyls a little bit. One of the most common mistakes that you may make when interpreting infrared spectroscopy involves carbonyl stretches. On this slide, you see the IR spectroscopy data tables corresponding to carbonyls that you can find on your organic chemistry lab notebook cover. You see how each type of carbonyl attached to a ring, an ester, an aldehyde, a ketone, an acid, an amide, and what's called a conjugated carbonyl, are given their particular ranges. The mistake you may make is believing that these values are exact values. From this table, you may believe that ketones appear at 1715, whereas carboxylic acids will always appear at 1710. This is not true. The potential danger of this table is you believing that there is such thing as a ketone stretch, or an ester stretch, or an aldehyde stretch. That carbonyl stretch tells you that there is a carbonyl in your molecule. It does not tell you what kind of carbonyl you have. Fortunately, you can narrow the options. If you look at this table, you see that there is a dividing line at 1700. These types of carbonyls above this line will always be above 1700. If you have an amide or a conjugated carbonyl, that stretch will appear below 1700. If you do not know what conjugated means yet, when I say conjugated carbonyl, I mean a carbonyl connected to a carbon-carbon double bond. Why do amides and conjugated carbonyls appear below 1700? This is because of resonance. Let me draw an amide here. R stands for some alkyl group. I can take this amide and draw a resonance structure where I take the lone pair on the nitrogen and move it this way to make this resonance structure. Why does this matter? Remember that the wave number of a stretch depends on the strength of the bond. You know that the stronger the bond, the higher the wave number it appears at. Remember from general chemistry that what a bond is actually like can be treated as a sort of average between all of its resonance structures. Let us look here particularly at the carbon-oxygen bond. In the resonance structure on the left, I have a double bond between the carbon and the oxygen. Double bond is a strong bond. In the resonance structure on the right, I have a carbon-oxygen single bond, which is weaker than the carbon-oxygen double bond. You may recognize that this resonance structure on the right is not a particularly good one, because it has charges. As a result, when averaging these resonance structures, this resonance structure on the right does not count for very much. However, it counts enough that the carbon-oxygen double bond in an amide is weaker than the carbon-oxygen double bond of most other carbonyls. It's the same argument if you have a conjugated carbonyl. If I take a conjugated carbonyl of some kind, and I do the same process, I can draw a similar resonance structure that has a carbon-oxygen single bond. As a result, after averaging these structures, the carbonyl in a conjugated carbonyl molecule is weaker than most other carbonyls. As a result, it shows up at a lower wave number. Before finishing up this slide, some of you may be wondering, okay, if that's true, why is it that esters don't do the same thing? Those oxygens and esters have lone pairs, why can't they move in the same way? This is because oxygen is much better at holding on to its lone pairs. As a result, the lone pairs on oxygen do not move in the same way. Therefore, the carbonyl in an ester is not weakened because of resonance. Using this information, we can now explain why we saw two carbonyl stretches in the IR spectrum for aspirin. Here at roughly 1700, we had two carbonyl stretches. We have one at approximately 1750, the one on the left, and one below 1700, the one on the right. What this tells me is that the one below 1700 belongs to either an amide or it is a conjugated carbonyl. And we see that in our molecule, we have a conjugated carbonyl. We have this carboxylic acid carbonyl directly connected to a carbon-carbon double bond. In contrast, we have this ester carbonyl, which is not conjugated. Therefore, it should appear above 1700, and indeed, it does, at around 1750. This is a fantastic example of how you can use the location of a carbonyl stretch to try and identify what kind of carbonyl it is. One final thing before we finish this webcast. Do you remember that carbonyls and carbon-carbon double bonds can overlap in this region? How can you tell the difference? As you can see, the carbonyl stretches tend to be stronger and more broad than the carbon-carbon double bond stretches. That will not always be the case, but if you have to make a decision, you can use size and shape to help you make that decision. That brings us to the end of this webcast. To recap, while you have access to the wave number values to many bonds via those tables I showed you at the beginning of this webcast, do not memorize all of them. Instead, memorize the 6 primary regions that we discussed. The first is the fingerprint region that is below 1500 wave numbers. This region is difficult to interpret, and I recommend that you avoid trying to use it in your infrared spectrum analyses. There is a carbon-carbon double bond region at approximately 1650 wave numbers. There's the carbonyl region at approximately 1700 wave numbers. We now know that the type of carbonyl matters a great deal. The stretch for most carbonyls will appear above 1700. Some carbonyls that are parts of amides or carbonyls that are conjugated, will appear below 1700 because of resonance. That resonance weakens the carbon-oxygen double bond, causing them to absorb light at lower wave numbers. There is the CC triple bond region at approximately 2200 wave numbers. Now remember, the CC triple bond stretch might not appear or might be very weak if the bond is too symmetric, so always be careful when working in this region. CH bonds appear around 3000 wave numbers, and you know that the type of CH bond determines where it appears. CH bonds that are sp3 hybridized are below 3000, CH bonds that are sp2 hybridized are above 3000. And finally, OH bonds and NH bonds tend to appear at around 3500 wave numbers. They also tend to be shaped differently than most other stretches. In the next webcast, you will see examples of all of these stretches. There, you will see how shape can be used to identify stretches, and you will see examples of how the same type of bond, say carbonyls or CH bonds, can appear in different locations depending on the type of carbonyl or CH bond.